Okay, this is the last lesson of the factors and products unit, and it's on what's called the difference of squares. And all that is a shortcut in a special case. Now let's take a look at one of these cases. It's 4x squared minus 9. Writing this in the form that we're used to, we can say this is 4x squared plus 0 times x. See, there's no x term in there, minus 9. From here, if we want to decompose it, what do? We look for two numbers that multiply to give us 4 times negative 9, which is negative 36. And those same two numbers need to add to give us the middle term, which in this case is a 0. What would those two numbers be? Well, it'll just be a positive 6 or a negative 6, because positive 6 times negative 6 is negative 36. Positive 6 plus negative 6 is 0. And what do we do with those two numbers? We use them to rewrite the middle term in the original expression. So we'd have 4x squared plus 6x minus 6x minus 9. From this point, we look at two pairs of binomials and factor the greatest common factor of each. For the first set, the 4x squared plus 6x, we can factor out a 2x, and then in brackets we'd have 2x plus 3. For the negative 6x minus 9, we can factor out a negative 3, and in brackets then we'd have a 2x plus 3 as well. We notice we have a common binomial, the 2x plus 3, we'll factor that out. So in one set we'll have 2x plus 3, and then it'll be multiplied by a 2x minus 3. And that would be your answer. Now let's compare the original expression to the factored form. And I'm going to write this a little bit differently, but just so we can compare the numbers more directly. So the original expression was 4x squared minus 9. And the factored form was a 2x plus 3 being multiplied by a 2x minus 3. So pause the video here and see if you can examine the original expression and factored form and see if there's any patterns that pop up into your head. So give yourself just a few seconds to think about that. If we compare the 4x squared to the 2x, you might notice that, well, if you took the square root of 4x squared, that's going to give you 2x. And if you compare 9 to 3, well, if you take the square root of 9, that gives you 3. And this pattern isn't a coincidence, so I want to attack this difference of squares problem in a different way and come up with a general solution for when we see differences of squares. Here's an example of differences of squares. You have two squares, one that has a length and width of b, and one that has a length and width of a. And if we were to determine the shaded region, what we're doing is taking the area of the big square and subtracting it, finding a difference between that area and the area of the little square. So we'll call this method the difference of squares method. We're just taking the area of the big square, that's a times a or a squared, and subtracting it from the area of the big square, b times b or b squared. Now let's look at the problem in a different way. What if instead of taking a difference of squares, we add up two rectangles? If we split the problem up like this, you can see we have a small rectangle in the bottom in green there, and a large rectangle in red on top. And if we add the area of those two rectangles together, we'll get the area of the shaded region. Now let's take a look at the dimensions of the green rectangle. The green rectangle has a length of b. But what about its width? Its width would be the longer side a minus the b. So the width in this case is a minus b. And then for the red rectangle, well, the red rectangle, its width is just a. But its width this time would be a minus b as well. So let's call this method the rectangle sums method and add up the areas of each. The area of the red rectangle we can write as a multiplied by a minus b, and we're going to add that to the area of the green rectangle, which we can say is b multiplied by a minus b. Notice that a minus b is a common factor in this case, so let's factor it out. A minus b will factor out, and then that can be multiplied by a plus b. So we just solved this problem in two different ways and got answers that, because they solved the same problem, must be equivalent. They're just written in different forms. First, you have a squared minus b squared equals the area of the shaded region, and also a minus b times a plus b equals the area of the shaded region. Therefore, both of those must be equal to each other. So let me write this down again. If you have a squared minus b squared, a difference in squares, you can write that as a minus b times a plus b. So if you have a perfect square minus another perfect square, your factored answer is going to be the square root of that perfect square minus the square root of the other perfect square times the square root of the perfect square plus the square root of the other perfect square. It's just a nice quick shortcut when you see a perfect square minus another perfect square. Okay, so let's take a look at a few examples. So x squared minus 64. These are both perfect squares because x times x is x squared. 8 times 8 is 64. It's a difference of squares because there's a minus sign there. So let's see. The square root of x squared equals x. The square root of 64 equals 8. So all we need to do, in one set of brackets, we'll have x minus 8, the other set x plus 8. Simple as that. Next example, 4y squared minus 25. The square root of 4y squared equals 2y. The square root of 25 equals 5. It's a difference of squares because you have that minus sign right there. Your factored form then becomes 2y minus 5 multiplied by 2y plus 5. And if you happen to write it as 2y plus 5 multiplied by 2y minus 5, that's the same thing as well. Two more quick examples, but don't forget our primary rule for factoring, which is factor out the greatest common factor first. Greatest common factor first. So for 9x to the power 4 minus 81, you can actually factor out a 9 first. Then you would have an x to the power 4 minus 9. Within the brackets, that's still a difference of squares, right? This can be written as x squared minus 3 multiplied by x squared plus 3. And then don't forget, you are still multiplying everything by 9 there. For 64y squared minus 9z squared, doesn't matter that there's two different variables. Both of those terms are perfect squares and they're being subtracted. So same rule applies. We'll take the square root of 64y squared, which is just 8y. We have the square root of 9z squared, which is 3z. So your factored form would just be 8y plus 3z multiplied by 8y minus 3z. And there you go. That's difference of squares. And that is the end of the factors and products unit.